Trinitrotoluene (ΤρΙnaɪtroʊʻtεljᵿ.iːn), or more specifically 2,4,6-trinitrotoluene, is a chemical compound with the formula C6H23CH3. This yellow-colored solid is sometimes used as a reagent in chemical synthesis, but it is best known as a useful explosive material with convenient handling properties. The explosive yield of TNT is considered to be the standard measure of strength of bombs and other explosives. In chemistry, TNT is used to generate charge transfer salts. While the two words are sometimes used interchangeably in common conversation, TNT is not the same as dynamite. A special formatting of nitroglycerin for use as an industrial explosive. History: TNT was first prepared in 1863 by German chemist Julius Wilbrand and originally used as a yellow dye. Its potential as an explosive was not appreciated for several years, mainly because it was so difficult to detonate and because it was less powerful than alternatives. TNT can be safely poured when liquid into shell cases, and is so insensitive that in 1910, it was exempted from the UK's Explosives Act 1875 and was not considered an explosive for the purposes of manufacture and storage. The German armed forces adopted it as a filling for artillery shells in 1902. TNT-filled armor-piercing shells would explode after they had penetrated the armor of British capital ships, whereas the British lyddite-filled shells tended to explode upon striking armor, thus expending much of their energy outside the ship. The British started replacing lyddite with TNT in 1907. The United States Navy continued filling armor-piercing shells with explosive D after some other nations had switched to TNT, but began filling naval mines, bombs, depth charges, and torpedo warheads with burster charges of crude-grade BTNT with the color of brown sugar and requiring an explosive booster charge of granular, crystallized grade A TNT for detonation. High explosive shells were filled with grade A TNT, which became preferred for this other use as industrial chemical capacity became available for removing xylene and similar hydrocarbons from the toluene feedstock and other nitrotoluene isomer byproducts from the nitrating reactions. TNT is still widely used by the United States military, as well as construction companies around the world. The majority of TNT currently used by the U.S. military is manufactured by Radford Army Ammunition Plant near Radford, Virginia. Preparation: in industry, TNT is produced in a three-step process. First, toluene is nitrated with a mixture of sulfuric and nitric acid to produce mononitrotoluene. The mount is separated and then renitrated to dinitrotoluene or DNT. In the final step, the DNT is nitrated to trinitrotoluene or TNT using an anhydrous mixture of nitric acid and oleum. Nitric acid is consumed by the manufacturing process, but the diluted sulfuric acid can be reconcentrated and reused. Subsequent to nitration, TNT is stabilized by a process called sulfitation, where the crude TNT is treated with aqueous sodium sulfite solution in order to remove less stable isomers of TNT and other undesired reaction products. The rinsed water from sulfitation is known as red water and is a significant pollutant and waste product of TNT manufacture. Control of nitrogen oxides in feed nitric acid is very important because free nitrogen dioxide can result in oxidation of the methyl group of toluene. This reaction is highly exothermic and carries with it the risk of a runaway reaction leading to an explosion. In the laboratory, 2,4,6-trinitrotoluene is produced by a two-step process. A nitrating mixture of concentrated nitric and sulfuric acids is used to nitrate toluene to a mixture of mono and dinitrotoluene isomers. with cooling to maintain careful temperature control. The nitrated toluenes are then separated, washed with dilute sodium bicarbonate to remove oxides of nitrogen, and then carefully nitrated with a mixture of fuming nitric acid and sulfuric acid. Towards the end of the nitration, the mixture is heated on a steam bath. The Trinitrotoluene is separated, washed with a dilute solution of sodium sulfite and then recrystallized from alcohol. Applications: TNT is one of the most commonly used explosives for military, industrial, and mining applications. TNT has been used in conjunction with hydraulic fracturing, a process used to recover oil and gas from shale formations. The technique involves displacing and detonating nitroglycerin in hydraulically induced fractures followed by wellbore shots using pelletized TNT. TNT is valued partly because of its insensitivity to shock and friction, which reduces the risk of accidental detonation, compared to other more sensitive high explosives such as nitroglycerin. TNT melts at 80 degrees Celsius, far below the temperature at which it will spontaneously detonate, allowing it to be poured as well as safely combined with other explosives. TNT neither absorbs nor dissolves in water, which allows it to be used effectively in wet environments. Additionally, it is stable compared to other high explosives. In order to initiate an explosion, TNT must first be detonated using a pressure wave from a more sensitive explosive called an explosive booster. Although blocks of TNT are available in various sizes, it is more commonly encountered in synergistic explosive blends comprising a variable percentage of TNT plus other ingredients. Examples of explosive blends containing TNT include Amatex, Amatol, Aminol, Baritol, Composition B, Composition H6, Cyclotol, Ednatol, Hexanite, Minol, Octol, Pentalite, Picrotol, Tetritol, Torpex, Tritonal. Explosive character. Upon detonation, TNT decomposes as follows: 2C7H5N3063N 2 plus 5H2O plus 7CO plus 7C2C7H5N3063N 2 plus 5H2 plus 12CO plus 2C. The reaction is exothermic but has a high activation energy in the gas phase. The condensed phases show markedly lower activation energies of roughly 35 kilocalories per mole due to unique bimolecular decomposition routes at elevated densities. Because of the production of carbon, TNT explosions have a sooty appearance. Because TNT has an excess of carbon, explosive mixtures with oxygen-rich compounds can yield more energy per kilogram than TNT alone. During the 20th century, amatol, a mixture of TNT with ammonium nitrate, was a widely used military explosive. Detonation of TNT can be done using a high-velocity initiator or by efficient concussion. For many years, TNT used to be the reference point for the figure of insensitivity. TNT had a rating of exactly 100 on the FOI scale. The reference has since been changed to a more sensitive explosive called RDX, which has an FOI of 80. Energy content. TNT is reported to contain 2.8 megajoules per kilogram explosive energy. The actual heat of combustion is 14.5 megajoules per kilogram, which requires that some of the carbon in TNT react with atmospheric oxygen, which does not occur in the initial event. The explosive energy utilized by NIST is 4,184 J per gram. The energy density of TNT is used as a reference point for many other types of explosives, including nuclear weapons, the energy content of which is measured in kilotons or megatons of TNT equivalent. For comparison, gunpowder contains 3 megajoules per kilogram, dynamite contains 7.5 megajoules per kilogram, and gasoline contains 47.2 megajoules per kilogram. Detection. Various methods can be used to detect TNT, including optical and electrochemical sensors and explosive sniffing dogs. In 2013, researchers from the Indian Institutes of Technology using noble metal quantum clusters could detect TNT at the sub-zeptomolar level. Safety and toxicity. TNT is poisonous, and skin contact can cause skin irritation, causing the skin to turn a bright yellow-orange color. During the First World War, munition workers who handled the chemical found that their skin turned bright yellow, which resulted in their acquiring the nickname "Canary Girls," or simply, canaries. People exposed to TNT over a prolonged period tend to experience anemia and abnormal liver functions, blood and liver effects. Spleen enlargement and other harmful effects on the immune system have also been found in animals that ingested or breathed Trinitrotoluene. There is evidence that TNT adversely affects male fertility. TNT is listed as a possible human carcinogen, with carcinogenic effects demonstrated in animal experiments, although effects upon humans so far amount to none, according to Iris of March 15, 2000. Consumption of TNT produces red urine through the presence of breakdown products and not blood as sometimes believed. Some military testing grounds are contaminated with TNT. Wastewater from munitions programs, including contamination of surface and subsurface waters, may be colored pink because of the presence of TNT. Such contamination, called pink water, may be difficult and expensive to remedy. TNT is prone to exudation of dinitrotoluenes and other isomers of trinitrotoluene. Even small quantities of such impurities can cause such effect. The effect shows especially in projectiles containing TNT and stored at higher temperatures, e.g., during summer. Exudation of impurities leads to formation of pores and cracks. Migration of the exudated liquid into the fuse screw thread can form via channels, increasing the risk of accidental detonations. Fuse malfunction can result from the liquids migrating into its mechanism. Calcium silicate is mixed with TNT to mitigate the tendency towards exudation. Ecological impact. Because of its use in construction and demolition, TNT has become the most widely used explosive, and thus its toxicity is the most characterized and reported. Residual TNT post-explosion can partition between multiple environmental, including water, soil, atmosphere, biosphere. The concentration of TNT in contaminated soil can reach 50 grams per kilogram of soil, where the highest concentrations can be found on or near the surface. In the last decade, the United States Environmental Protection Agency has declared TNT a pollutant whose removal is priority. The US EPA maintains that TNT levels in soil should not exceed 17.2 gram per kilogram of soil and 0.01 milligrams per liter of water. Aqueous solubility dissolution involves how rapidly solid TNT in contact with water is solubilized. The relatively low aqueous solubility of TNT causes the dissolution of solid particles to be continuously released to the environment over extended periods of time. Studies have shown that the TNT dissolved slower in saline water than in fresh water. However, when salinity was altered, TNT dissolved at the same speed. Because TNT is moderately soluble in water, it can migrate through subsurface soil, and cause groundwater contamination. Soil adsorption. Adsorption measures the distribution between soluble and sediment-sorbed contaminants following attainment of equilibrium. Explosives such as TNT and its transformation products are known to adsorb to surface soils and sediments, where they undergo reactive transformation or remain stored. The movement or organic contaminants through soils is a function of their ability to associate with the mobile phase and a stationary phase. Materials that associate strongly with soils move slowly through soil. Materials that associate strongly with water move through water with rates approaching that of groundwater movement. The association constant for TNT with the soil is 2.7-11 liters per kilogram of soil. This means that TNT has 1 to 10-fold tendency to adhere to a soil particulates than not when introduced into the soil. Hydrogen bonding and ion exchange are two suggested mechanisms of absorption between the Nitro functional groups and soil colloids. The number of functional groups on TNT influences the ability to adsorb into soil. Adsorption coefficient values have been shown to increase with an increase in the number of amino groups. Thus, absorption of the TNT decomposition product 2,4-diamino-6-nitrotoluene was greater than that for 4-amino-2,6-dinitrotoluene, which was greater than that for TNT. Lower adsorption coefficients for 2,6-DNT compared to 2,4-DNT can be attributed to the steric hindrance of the NO3 group in the ortho position. Research has shown that in freshwater environments, with the high abundances of California 2+, the absorption of TNT and its transformation products to soils and sediments may be lower than observed in a saline environment dominated by K+ and Na+. Therefore, when considering the adsorption of TNT, the type of soil or sediment and the ionic composition and strength of the groundwater are important factors. The association constants for TNT and its degradation products with clays have been determined. Clay minerals have a significant effect on the absorption of energetic compounds, and can be ranked, as seen in Table 2. It should be noted that soil properties, such as organic carbon content and cation exchange capacity, had significant impacts of the adsorption coefficients reported in the table below. Additional studies have shown that the mobility of TNT degradation products is likely to be lower than TNT in subsurface environments where specific adsorption to clay minerals dominates the absorption process. Thus, the mobility of TNT and its transformation products are dependent on the characteristics of the sorbent. The mobility of TNT in groundwater and soil has been extrapolated from absorption and desorption isotherm models determined with humic acids in aquifer sediments and soils. From these models, it is predicted that TNT has a low retention and transports readily in the environment. Compared to other explosives, TNT has a higher association constant with soil, meaning it adheres more with soil than with water. Conversely, other explosives, such as RDX and HMX with low association constants, can move more rapidly in water. Chemical breakdown: TNT is a reactive molecule and is particularly prone to react with reduced components of sediments or photodegradation in the presence of sunlight. TNT is thermodynamically and kinetically capable of reacting with a wide number of components of many environmental systems. This includes wholly abiotic reactants, like photons, hydrogen sulfide, Fe2+, or microbial communities, both oxic and anoxic. Soils with high clay contents or small particle sizes and high total organic carbon content have been shown to promote TNT transformation. Possible TNT transformations include reduction of 1, 2, or 3 nitromoieties to amines and coupling of amino transformation products to form dimers. Formation of the 2 monoamino transformation products, 2-ADNT and 4-ADNT, are energetically favored, and therefore are observed in contaminated soils and groundwater. The diamino products are energetically less favorable, and even less likely are the triamino products. The transformation of TNT is significantly enhanced under anaerobic conditions as well as under highly reducing conditions. TNT transformations in soils can occur both biologically and abiotically. Photolysis is a major process that impacts the transformation of energetic compounds. The alteration of a molecule in photolysis occurs in the presence of direct absorption of light energy by the transfer of energy from a photosensitized compound. Phototransformation of TNT results in the formation of nitrobenzenes, benzaldehydes, azo-dicarboxylic acids, and nitrophenols. As a result of the oxidation of methyl groups, reduction of nitro groups, and dimer formation, evidence of the photolysis of TNT has been seen due to the color change to pink of the wastewaters when exposed to sunlight. Photolysis was more rapid in river water than in distilled water. Ultimately, photolysis affects the fate of TNT primarily in the aquatic environment but could also affect the reaction when exposed to sunlight on the soil surface. Biodegradation. The lignin-lytic physiological phase in manganese peroxidase system of fungi can cause a very limited amount of mineralization of TNT in a liquid culture, though not in soil. An organism capable of the remediation of large amounts of TNT in soil has yet to be discovered. Both wild and transgenic plants can phytoremediate explosives from soil and water.